Hello everyone, I hope you're all doing well and having a great day. So today's video is all about pure mathematics 4, proof by contradiction, a topic many of you have struggled with and have been requesting us to cover for the past few months. With upcoming sessions in May 2025 and October 2024, and even for students appearing in future sessions, this video will be extremely helpful. We have solved all the proof by contradiction questions from the past papers starting from October 2020 up to the latest January 2024 paper. So without further delay, let's get started and master this topic once and for all. And so proof by contradiction is, first of all, we need to assume the opposite of the statement. So the base value is n. So if n is even, n cube is even. This is the statement, so we need to assume the opposite of this statement. We will assume that you need to write this, is that assume n is odd, so n cube will be even. Now we need to carry out our calculation. So if n is odd, we can write an odd number like this, where you go n equals 2k plus 1. If this was even, we could have written it like this, n equals 2k. So now we know that n cube will be equal to 2k plus 1 whole cube. Now you need to prove that n cube is even. So if we use the formula a plus b whole cube to expand this, we can write this as 2k cubed plus 3 times 2k whole square times b plus 3a and b squared plus b cubed. So now this will give us a value of 8k cubed and plus 12k squared plus 6k plus 1. Now if n cube is even, which means you can divide it by 2, because we can divide even numbers by 2. So even numbers are always divisible by 2. So if we take 2 common from this part, this will give us 4k cubed plus 6k square plus 3k. And we have plus 1 at the end of the expression. Now as you can see that only this expression can be divided by 2. There is a plus 1 at the end of it, so this contradicts our assumption. It's that n cube will not be even. So at the end, we can end with a conclusion that this contradicts our assumption, or you can just write it like this, is that which is not even. And then you can jump to the conclusion. Thus, this contradicts our assumption. So if n cube is even, then n is also even. So if n cube is even, n is also even. So that is it for this question. And moving on to the next question. This is a question from January 2021, question 3. So this is very simple. We need to prove by contradiction that there is no greatest odd integer. So first of all, we need to assume the opposite. We need to assume that there is a greatest odd integer. Assume there is a greatest odd integer. and that integer will be denoted by, let's say it's n. So the greatest odd integer is n. Now, if I look at it like a series, let's say n is an odd integer, the next one will be n plus 1, which will be an even integer. And the next value will be an odd integer, which is n plus 2. Now, as you can see that if you add plus 2 to n, you'll get the next odd integer. So this actually contradicts our assumption that there is a greatest odd integer, because there is no greatest odd integer. If you add 2 to an odd value, you'll get the next odd value. So there's also an odd integer. Now we can say that thus this contradicts our assumption. So there is no greatest odd integer. There will always be another value after that. So there's no greatest odd integer. So that is it for this question. Now moving on to the next question. This is a question from May 2021, question 9, part 2. Now, given that n belongs to natural numbers, prove by contradiction that if n square is a multiple of 3, then n is also a multiple of 3. So the base value is n. So we need to assume the opposite of this base value. So we need to assume that n is not a multiple of 3. So assume n isn't a multiple of 3. N isn't a multiple of 3, so n square will be a multiple of 3. N square is a multiple of 3. Now, since n isn't a multiple of 3, if n was a multiple of 3, we could have wrote this as 3k. Now, since this is not a multiple of 3, you can add 1 to it and make it not a multiple of 3. You can add 1 or you can also add 2, but I prefer 1. But if you add 3 to it, this would be a multiple of 3. So now let's find out the value of n square. So we can write n square as 3k plus 1 whole square. So this is equals to 6k square plus 6k plus 1. Now, since we're proving that n square is a multiple of 3, we need to take 3 common. But we can take 3 common from these two expressions only. So it's 2k square plus 2k plus 1. Now, as you can see that this contradicts our assumption that if n is not a multiple of 3, n square will also not be a multiple of 3. So you can write it, you can add a side note by the side, which isn't a multiple of 3. Now you can end with a conclusion. Thus, this contradicts our assumption. So if n is a multiple of 3, n squared will also be a multiple of 3. N squared. So that is it for this question. Now moving on to the next question. This is a question from October 2021, question 10. So in the first part, a student's attempt to answer the question proved by contradiction that if n cube is even, then n is also even. So the assumption will be that n is odd, but n cube is even. So that's the assumption. Now line 5 of the proof is missing. Okay, so this line is missing. Now we need to complete this proof by filling in line 5. So in line 5 is that they have said that n is equals to 2p plus 1. Now they will find out the value of n cube. Now in this part, since they're talking about that n cube is even, we need to take 2 common. So this will be 4p cubed plus 6p squared plus 3p plus 1. Because even numbers can be divided by 2, but there's a plus 1 at the end. So now we can say that which is odd. So that's the end of the proof. Now in the second part, we need to prove by contradiction that cube root over 2 is irrational. So it's very simple that the assumption will be cube root over 2 is rational. So let's first write down the assumption. Assume cube root over 2 is rational. Now, what does a rational or an irrational number means? A rational number means that you can write the number in a fraction form, which is, let's say we have the number 4, you can write this as 8 over 2. If there's the number 5, you cannot write this as 5 over 1. This does not prove that 5 is a rational number. 5 is an irrational number. The denominator must be anything but 1. So since cube root over 2 is rational, we can write this as a over b, where a and b are constants. And if you take this cube root and move it to the right hand side of the equation, this will become o cubed. So this is actually a cubed over b cubed. Now if you make a cubed the subject, this becomes 2b cubed. Now since there's a 2 at the front and a cube is equals to twice of b cubed, we can say that hence a cube is even. A cube is even. So now you can say that a is also even. So we can say that a is twice of k. So we can replace a cube with twice of k whole cube, and this is equals to twice of b cubed. So this is 8k cubed equals twice of b cubed. So now we can write b cubed as 4k cubed. Now we can say that b cubed is also even. So b cubed is also even. Therefore, b is also even. So this is the mathematical part of the contradiction. This contradicts our assumption because a and b is not in its simplest form as they both have a factor of 2. So since a and b both have a factor of 2, a divided by b is not in its simplest form. So this contradicts our assumption. Therefore, cube root 2 is irrational. So cube root 2 is irrational. So that is it for this question. Moving on to the next question. This is a question from January 2022. Question 6. Moving on to the next question. This is a question from January 2022. Question 6. So 3 consecutive terms in a sequence of real numbers are given by, so these are consecutive terms. This is the first term, second term, and third term, where k is a constant. Use proof by contradiction to show that this sequence is not a geometric sequence. So our assumption will be the opposite of that. We will assume that the sequence is geometric. So assume the sequence is geometric. Now, since this is a geometric series, we can say that the common ratio is equal to the second term divided by the first term. So it's 1 plus 2k over k. Or we can also write this as the third term divided by the second term. This will give us the same answer. So it's 3 plus 3k over 1 plus 2k. Now we can solve this equation. So solving this equation will give us, if we cross multiply, let's multiply this with this and this value with this value. So this is 4k squared plus 4k plus 1 equals 3k squared plus 3k. And if we simplify this, this will be k squared plus k plus 1 equals 0. Now, if this is a geometric series, solving this equation will give us a value for k. But as you can see that the b square minus 4ac, let's calculate the value of b square minus 4ac, which is 1 minus 4 times 1, which is -3. So this gives us a negative value of the discriminant. So we can say that since b squared minus 4ac is less than 0, this contradicts our assumption. So this is our conclusion, that since b squared minus 4ac is less than 0, this contradicts our assumption, so the sequence is not geometric. So that is it for this question. Moving on to the next question. This is from May 2022, question 9. We need to use proof by contradiction to show that when n is an integer, n squared minus 2 is never divisible by 4. So the assumption is pretty simple. So we need to assume that n squared minus 2 is divisible by 4. Divisible by 4. So since this is divisible by 4, which means n squared minus 2 is a multiple of 4. So we can say that n squared minus 2 is equals to 4k. since this is divisible by 4, where k is a constant. Now, if we make n squared the subject, we get 4k plus 2. Now, what we can do is that we can take 2 common to show that n squared is also even. So, n squared is even, therefore n will also be even. So we can write n squared as twice of k whole squared equals 4k plus 2. Or we can just say that since n squared is even, since n is even, so we can say that n squared minus 2 will be equal to twice of k whole squared minus 2. Now, if we simplify this is 4k squared minus 2. If we take 2 common, or if we take 4 common, we only get k squared minus 2. Or you can just take 2 common, so it's 2k squared minus 1. Now, as you can see that this is an n squared minus 2 is an even number, because this is divisible by 2. This is not divisible by 4. So this contradicts our assumption that n squared minus 2 is not divisible by 4. So you can just add a side note that which isn't divisible by 4. Now you can say that this contradicts our assumption. So n squared minus 2 is never divisible by 4. So that is it for this question. And moving on to the next question. This is a question from January 2023, question 9. So this question is actually identical to the previous question we solved from October 21. So a student was asked to prove that for p belongs to natural numbers, that if p cube is a multiple of 3, then p must be a multiple of 3 also. Now, the assumption would be that p is not a multiple of 3, but p cube is a multiple of 3. So that is the assumption. So let p equals 3k plus 1. Okay. So they have said that p equals 3k plus 1. That was for 3k plus 1. Now, they did not do another calculation. I mean, this calculation is not necessary, but for this proof, it's necessary, because there's 3 marks for the calculation. Now, for part B, so for part A, another thing that since p is not a multiple of 3, p can also be written as 3k plus 2. If we add 3 to it instead of 2, this would have been a multiple of 3. So now let's find out the value of p cubed, which is 3k plus 2 whole cubed. So this would be equal to 27k cubed. If we use the expansion for a plus b whole cubed, this will be 27k cubed plus 54k squared plus 36k plus 8. Now let's take 3 common and prove, and let's contradict this with the assumption So if we take 3 common, you can divide 27k cubed by 3. So it will give us 9k cubed, and dividing this will give us 18k squared, and dividing this will give us 12k. Now you cannot divide 8 by 3. So you can leave the 8 at the side. Now you can say that this is not a multiple of 3. Isn't a multiple of 3. So does this contradicts our assumption? So this is the remaining part of the proof. Alright, so now moving on to the second part, is that we need to prove that cube root over 3 is an irrational number. So we have covered this before that. Let's just first write down the assumption. So assume the opposite, which is assume cube root over 3 is a rational number. Now, since this is a rational number, we have talked before about this, that this can be written as a over b, where a and b are constants, and this fraction must be in its simplest form for it to be rational. Now let's find out if this fraction is in its simplest form or not. Now if you take this cube root 3, if you take this cube root, move it to the right hand side of the equation, so this becomes whole cubed. So this is a cubed over b cubed. Now if you make a cubed the subject, this becomes 3b cubed. Now since there's a 3 at the front, as a cubed can be written as 3b cubed, we can say that a cube is a multiple of 3. A cube is a multiple of 3. Now if a cube is a multiple of 3, therefore a will also be a multiple of 3. So now we can write a as 3 times k. So we can write a cube as 3k whole cubed. You don't need to write this in the answer script. So that's 3k whole cubed equals 3b cubed. So this is equals to 27k cubed over 3 equals 3b cubed. So if we make 3 b cubed, this b cubed the subject, this becomes 9 times k cubed. So this can be written as 3 times 3k cubed. So we can say that b cubed is also a multiple of 3. So hence b cubed is also a multiple of 3. So b will also be a multiple of 3. So now this contradicts our assumption is that a by b is not in its simplest form. So we can write, since a and b both have a factor of 3, A divided by B is not in its simplest form. So this contradicts our assumption. So now we can say, therefore, cube root over 2 is irrational. Cube root over 3, not 2, sorry for that. So cube root over 3 is irrational. So that is it for this question. So moving on to the next question. This is from May 2023, question 7. So this question is actually the steps are identical to the previous ones. We need to prove by contradiction that root over 7 is irrational. So the assumption will be pretty simple. So we need to assume that root over 7 is rational. So since this is rational, root over 7 can be written in a fraction format, which is a divided by b, where a and b are constants, and this fraction must be in its simplest form. Now, if we take this root over to the right hand side of the equation, this becomes whole squared. So this is basically a squared by b squared. So if we make a squared the subject, this becomes 7b squared. Now we can say that a squared is a multiple of 7 because there's a 7 at the front. So a squared is a multiple of 7. Which means that a is also a multiple of 7. So we can write a as 7k. So this is 7k whole squared equals 7b squared. So this can be written as 7 squared k squared equals 7b squared. Now if we make b squared the subject, this will become 7 times k squared. So now we can say that b squared is also a multiple of 7. B squared is also a multiple of 7. So b will also be a multiple of 7. So this contradicts our assumption. So now we can end with a conclusion that since a and b both have a factor of 7, a divided by b is not in its simplest form. So this contradicts our assumption, therefore root over 7 is irrational. So that is it for this question. Now moving on to the next question. This is October 2023, question 4. We need to prove by contradiction that for all positive numbers k plus 9 over k is greater than or equal to less than 6, equal to 6. Okay, so the assumption would be pretty simple. Since this is equal to or greater than, we need to assume the complete opposite. So we need to assume k plus 9 over k is less than 6. Now let's see what we can do with this inequality. We can multiply this whole inequality by k, so this becomes k squared plus 9 less than 6k. And we can bring this 6 to the left hand side of the inequality, so this becomes negative 6k plus 9 less than 0. Now let's bring this to a perfect square format. So this becomes k minus 3 whole squared minus 9 plus 9. Minus 9 plus 9 is 0, so this is less than 0. Now this contradicts our assumption, but you need to give an explanation. So the conclusion will be, since k minus 3 whole square is always greater than or equal to 0, because this can never be negative, since there's a square at the front, and this could be equal to 0 because k could be equal to 3, so 3 minus 3 whole square is equals to 0. And if k is negative 4, so this becomes negative 7, and negative 7 whole square is 49, which is a positive value. So k minus 3 whole square will always be greater than 0 or equal to 0. So this contradicts our assumption. It's that k minus 3 cannot be less than 0. So k plus 9 over k is greater than or equal to 6. So that is it for this part. Now moving on to the next part, show that the result in part A is not true for all real numbers. So it's pretty simple because this is kind of like a trial and error method. It's that take k equals 0, for example, and substitute it in this expression. So this becomes 0 plus, okay, k cannot be 0. So let's take k equals 1, for example. So this becomes 1 plus 9 over 1, which is basically 1 plus 9 over 1, which is 10, which is greater than 6. Okay, let's take a negative value. Let's take k equals negative 3. So if k is equals to negative 3, it's negative 3 plus 9 over negative 3. So this is negative 3, which is negative 6. So minus 3. So minus 3 and minus 3 is equals to minus 6, which is less than 6. So this contradicts the, this contradicts this inequality. So that is it for part B. So is that when k equals negative 3, so the answer is negative 6, which is less than 6. So now you can end with a conclusion that the inequality in part A is not true for all real numbers. So that is it for this question. Now moving on to the next question. This is a question from January 2024. Question 8. So we need to use proof by contradiction to prove that the curve with equation this has no stationary points. So the assumption will be simple. We need to assume the opposite, that assume the curve has a stationary points. Assume the curve has a stationary points, which means dy over dx will be equal to 0. So if we differentiate this first term, it will be 2, and differentiating the second term will give us 3x squared, and differentiating cos x will give us negative sine x. So this is equals to 0. Now if we make sine x the subject, sine x can be written as 3x squared plus 2. Now as you can see that for all values of x, 3x squared plus 2, 3x squared plus 2 will always be greater than, it can be 0. Wait. So it can be 0. So 3x squared plus 2 will always be greater than 2 or less than, okay. So 3x squared plus 2 will always be greater than 2 or 3x squared 2. 3x squared plus 2 will always be less than negative 2. Less than or equal to. Now sine x must be less than 1 but greater than negative 1. But as you can see that if you substitute any values of x into this equation, it will either give you an answer of 2 or it will give you an answer of, okay, so forget about the part I've written in this region. Let's just start over. Let's say if I substitute the value of x equals 0 into this equation, we get sine x equals 2. Or if I substitute a negative value of x, we will still get a positive value since there's a positive sign, since there's a square at the front. So we can make an assumption. It's that 3. It's not an assumption. It's just a fact that 3x squared plus 2 will always be greater than or equal to 2. But sine x must be less than 1 but greater than minus 1. Sine x cannot be greater than 2. It will give you it will not give you any answer. So this contradicts our assumption. So the curve has no stationary points. So that is it for this question. So hopefully you found this video helpful. We have covered every proof by contradiction question up to January 2024 in this video. For the May 2024 and October 2024 questions, you'll find the complete solutions in our Pure Mathematics 4 full paper solving videos available on our YouTube channel. As for the January 2025 paper, we will upload the complete solved version before your exam, so make sure to subscribe and stay tuned. If you'd like to complete the full syllabus and practice all questions with me, join our high impact crash course for October 2025 and the 2026 sessions or any upcoming sessions. And if you're a May 2025 candidate with only a month or 2 left, don't worry, join our question papers marathon course to strengthen your preparation by solving all papers from January 2020 to January 2025 with us. To join, just simply message us on our Exam Essentials Facebook page or WhatsApp us using the number provided in the description. So best of luck with your preparation.